Let's talk about how Slack builds AI features for millions of its enterprise users without ever letting customer data leave the infrastructure. This is a real world case study and I have broken it down to three steps that you can see on the screen right now. On the left, we have step 1, which covers the core concepts and theory. In the middle, we have step 2, which shows you the actual code patterns. And on the right, we have step 3, which is a real world architecture with system diagrams. So let's start with step 1. Let's talk about the fundamental challenge of building AI in enterprise environments. When you integrate large language models into enterprise products, you face a core problem. These models deliver powerful capabilities, but the standard integration pattern requires sending customer data to third party hosted services. For companies operating under compliance frameworks like FedRAMP, HIPAA, or SOC 2, this creates what seems like a pretty impossible trade off. You either get AI capabilities and break compliance, or you maintain compliance and skip AI entirely. However, Slack refused to accept this trade off. They needed AI features for their users, but they could not compromise on data sovereignty. So they built an architecture that delivers both. Let's talk about the foundations of Slack's approach here, which is the four principles they established before writing any code. The first principle states that the customer data never leaves the trust boundary, which what this means is that it eliminates the standard approach of calling hosted LLM APIs because every one of those calls will send data outside your infrastructure. The second principle is that they do not train on customer data. This eliminates fine tuning and model customization because training creates risk that customer data gets encoded into model weights. The third principle says that the AI should operate only on the data the user can already see. This eliminates building separate data pipelines for AI that might have different permission models than the main application. The fourth principle requires that all existing compliance offerings extend to AI features. This eliminates building parallel security systems and ensures that existing enterprise controls automatically apply to this use case as well. These four constraints sound pretty simple, but they eliminate the most standard approaches to LLM integration. Every architectural decision was tested against these principles as well. Now let's talk about the trust boundary architecture, which is a key insight that makes this architecture possible. A trust boundary defines infrastructure you control versus infrastructure you rely on through contracts and vendor promises. Inside your own boundary, you enforce your own security policies. Outside your boundary, you can depend on someone else's promises. In traditional LLM integration, every API call sends customer data outside your trust boundary. The model provider's security practices becomes your risk and you have no control over data retention or whether that data gets used for training. Slack approach flips this model. They use what they call an escrow VPC arrangement where the cloud provider hosts the model weights inside Slack's own infrastructure. The model provider licenses their weights but never actually accesses the deployment or the customer data flowing through it. The result here is that the customer data never exits the Slack's infrastructure. The LLM runs inside the trust boundary and not outside it. Now let's talk about why Slack chose retrieval augmented generation, which is RAG, over fine tuning for their models. With fine tuning, the model learns from your data permanently. That data gets encoded into model weights, which creates risk that information could leak across different customers or workspaces. The privacy guarantee with fine tuning is relatively weak. With RAG, however, every request is completely faceless. You include all the context needed within each request, and the model retains nothing between these requests. There is zero data retention in the model layer, which means there is no risk of cross tenant data leakage. The privacy guarantee in this case is pretty strong. Slack chose RAG because the privacy guarantees outweighs the latency trade-off. Yes, RAG requests is slower because you're sending more tokens, and yes, you need models with large context windows as well. However, the architecture benefit of true statelessness is what worth the extra costs. Now let's talk about the critical design decision around access control, which is enforcing permissions at the data retrieval layer rather than filtering outputs after generation. When a user requests a channel summary, the system fetches messages using that specific user's access control list. If the user cannot see certain messages in normal Slack usage, those messages are not never sent to the LLM in the first place. This is fundamentally different from generating a response and then filtering out sensitive information afterward. By the time any data reaches the model, it has already been scoped to what the user is allowed to see. The AI cannot accidentally reveal information because it never receives information the user should not have access to. This approach also reuses existing Slack infrastructure rather than building parallel permission systems. Now let's talk about the final concept which combines ephemeral outputs with data loss prevention. Slack AI outputs are not stored anywhere. When you request a channel summary, the system generates a response that exists only in memory for your current session. There is no database to generate summaries. There is no cache of previous AI responses as well. The minimum necessary storage is absolutely zero. But there's additional layer here around compliance. Slack tracks which source messages were used to create each AI output. When a message gets deleted because of DLP policy, any summaries that reference the message are automatically invalidated. This extends existing compliance controls to AI features without requiring administrators to learn new tools. If DLP already protects sensitive content in messages, it automatically protects any AI generated content driven from those messages. Now let's move to step 2 and look at how these concepts can translate into actual code. Now let's talk about the core code pattern which makes secure AI enterprise AI possible, which is ACL-scoped data retrieval. Looking at the get channel context function on screen, you can see the critical sequence. First, we retrieve the user's access control list by calling ACL service.getUserACL with the user ID parameter. Then, before fetching any data at all, we check whether that user can access the requested channel. If the permission checks fails, we raise the permission denied error immediately. We never touch the data layer for users who should not have access. When the permission check passes, we call the message store.getMessages and we pass the user ACL directly to the data layer. This is a key insight here. The ACL is not checked after we retrieve messages. The ACL is passed into the query itself, so we can only ever retrieve messages this user is allowed to see. This is the same code path that renders messages in the Slack user interface. By reusing the existing infrastructure, we guarantee that AI and the main application have identical permission behavior. Now let's talk about how all these components connect in the production summarization flow. Looking at the channel summarization class on screen, you can see it takes 6 dependencies in its constructor: the ACL message, the ACL service, the message store, the context builder, the LLM client, the content tracker, and response manager. The summarize method shows the complete sequence. The first step calls get for user on the message service, which uses the ACL scope retrieval pattern we just discussed. The second step calls the build method on the context builder, which assembles the messages into a prompt that fits within the model's token budget. This returns both the context string and the list of source message IDs. The third step is where it calls the generate on the LLM client, passing the summary prompt and context. This client is configured to only communicate with models inside the trust boundary. The fourth step is where it registers the derived content with the tracker, linking this new summary to all the source message IDs that went into it. This enables the DLP invalidation we discussed earlier. Finally, the fifth step creates an ephemeral response that exists only in memory and returns the session key to the caller. The summary itself is never returned to the disk. This single method demonstrates all 5 concepts from step 1 working together in production code. Now let's move to step 3 and see how this looks at the infrastructure level. Let's talk about the high-level architecture that makes all of this possible. Looking at the diagram on screen, you can see 3 distinct zones. At the top outside the trust boundary, we have Slack clients. These are the web browsers, mobile applications, and desktop applications that users interact with. Everything else sits inside what labeled as Slack trust boundary. Within that boundary, there are 2 separate VPCs. The first is the Slack VPC, which contains the web and API servers that handle user requests, the data stores, and the indices that hold customer messages, and the ACL service as well that manages its permissions. The second is the AWS escrow VPC, which contains the foundation models. This is a key architecture element. The LLM runs inside the Slack's trust boundary, not outside it. Now, if you notice the arrows, users connect to the API servers. The API service communicates with the data store, the ACL service, and the LLM, but there's no arrow from the LLM to anything outside the trust boundary. Customer data flows between Slack systems and never exits to the third parties. Now let's talk about what actually happens when a user clicks summarize, walking through the sequence diagram on the screen. The flowchart starts with when a user sends a summarize channel request to the API server, and then the API service first action will be to call the ACL service to get the user's permissions. Once the API server calls the message store, passing the ACL along with the request. The message store then returns only the messages this user is permitted to see. Then the API server calls the context builder, which assembles those messages into a prompt and returns both the context and the list of source IDs. Next, the API server sends the generate request to LLM running an escrow VPC. The LLM returns in the summary text. After receiving the summary, the API server registers this derived content with the content tracker, linking it to the source message IDs for future DLP compliance. Then the API server creates an ephemeral response through the response manager, which returns the session key. Finally, that session key will go back to the user, which can retrieve the summary for the duration of the session. This sequence shows that every security and compliance control is there, executed in the correct order for every single summarization request. So to summarize now, this is how Slack builds enterprise AI without compromising on data sovereignty. The core pattern here is that hosting models inside your trust boundary using an escrow VPC arrangement, enforcing permissions at the data retrieval layer before anything reaches the AI, and using RAG for stateless requests handling with Ephemeral outputs. If you are building AI features for enterprise customers, you should definitely consider following this architecture pattern that Slack follows as well.